Welcome everybody. So we're here on our next series of CPD in 43 with MACH Group. Ze Nunes and Josh Childs from the company are here to talk about optimizing building physics design. Two very contrasting projects, one which is a small budget of £140,000 and one which is a very large budget of £140 million. And they want to talk about sort of the various areas that they get involved on those contrasting projects, and also what level of work that they end up doing on both, and sort of to show you the similarities, because obviously the basis of what is required is relatively similar. It just becomes more complex with more. I just want to quickly show you a couple of our future events. So we've got View City on Wednesday, 19th of May, which is really interesting 3D visualization of many cities in the UK in particular, where you're able to sort of analyze projects within the current space and also alter it to look at what might have been approved and how that may affect your planning, your potential proposal. And then moving forward, on the 2nd of June, we've got one from Cinema Works, which is designing home cinemas and media rooms. So I will hand this over to Ze and Josh, and we will make a start. So if I just stop sharing, and I'll hand it straight over to you, Ze. I'm going to be here in the background, but I will be muting myself and turn off my video.
No worries. Well, firstly, thank you all for attending. As pointed out by Usman, it's myself and Josh undertaking this presentation, and we'll start it here. I take it everybody can see my screen?
Yes. Okay.
Yes, we can. Yeah.
Perfect.
We can see that.
Good stuff. So really, what is our role? I mean, our goal at MACH is to be driving sustainability forwards. MACH started off as an acoustic consultancy. It's now turning into a multidiscipline practice, or has turned into a multidiscipline practice, and still has a strong bent on acoustics. And really, how does acoustics affect our world, and how do we use acoustics to produce a more sustainable, greener future for us all? I think this is probably the best example of how things are tied together. So this is an illustration that a student produced for us a number of years ago, but it's quite clever, where you have daylighting and solar gains effectively govern your window size. Your solar gains governs your heat as well as your occupancy. Your heat then needs to be balanced against your ventilation rates, and your ventilation rates are proportional to what type of ventilation you're using. But the more ventilation you need, the bigger the open area in the facade, and therefore you have an acoustics challenge. If you add cooling, you're then altering this, but you're then burning energy, and the cooling would come in here somewhere, and therefore you can see that the cooling and the acoustics are linked together. So the services that we provide is with acoustic consultants. We do overheating analysis, we do daylighting analysis, and we do Part L compliance testing, as well as passive house and air testing and sound testing at the completion of a building. These services are important to MACH because by undertaking them all under one roof, it enables us to offer a slightly different service to some of our competitors, which we'll come on to. So we're formed from acoustic consultants, which is our core. We employ architects. That helps us to communicate and understand how buildings perform and how to draw buildings and how to work with teams. We do quite a lot of teaching at various universities, Bath, Bristol Uni and UWE, as well as other universities. And then we do dissertations with the students to help us develop our skills and understanding of different aspects. We've got accredited Part L and SAP testers and SBEM assessors. We also, interestingly, have some software engineers. We have 2 software engineers, and they optimize the way that we work and so forth. We have a range of staff, probably 5 or 6 now, who have an MSc from Bath University in environmental design, which are running our thermal models and daylighting assessments and so forth. And as well, we have qualified passive house testers. So we create low carbon buildings. If you really want to motivate us, this is the way forward. One thing I do like about low carbon buildings is they also tend to be the more cost effective buildings. So therefore contractors and clients have a strong interest in going green. We do this, and this is the basis of this presentation, through modelling and a holistic approach. And what we're going to try and show you is how early modelling and how early analysis at the beginning of a job, if it's carried out in tandem with all the other disciplines, can add significant benefits to the projects that we get involved in. We have a good working relationship with both designers and contractors. For us, it's about taking the building out the ground as well as designing the building, so we value both input from both teams equally. And we work in a collaborative way. You know, it's fundamental to understand everybody's discipline and respect everybody, and try to move forwards in that manner. So this is just reiterating the challenge that we've got. You know, it's obvious that things are changing. The weather is getting hotter. If we don't do something about that, we're going to get ourselves into serious trouble. As the weather gets hotter, we need to ventilate more. As we ventilate more, we open more windows, and then we've got a bigger acoustic.
Ze, I think you're muted. Sorry about that.
Okay, I'm very sorry. I'll start again.
Which bit were
we muted from the beginning?
No, it literally just a couple seconds ago.
Okay, not now. So we were here.
Yeah.
Okay. Hear me?
Yes.
Yeah.
Cool. So what do we deliver? This is one of our key things. We get absolutely frustrated to kingdom come whenever we hear a building physics guy saying that the thermal modeler is on holiday. It's going to take 6 weeks to do this, X, Y, Z. That's, in our opinion, unacceptable. Early modelling at the beginning of a project is absolutely fundamental. Coordinated design, so bringing the acoustics, thermal, lighting together, is core. Holistic, in some ways the same thing. We have to share and balance each discipline together to get the optimum design. And this is really where I think that we thrive and where we work hard. We use a lot of high-powered computational analysis to do the work that we're doing. Instead of using it on, well, we could model it, we'll wait till we model it, we'll wait till stage 4, X, Y, Z, we just chuck mathematics at it from the very beginning. And the idea is that we offer this holistic tie-together approach. So before we start that, I just want to explain one of the ways that we do this analytics. We produce what we call the one model, which I'll introduce very quickly. The one model allows us to do overheating analysis. It also allows us to do acoustics, acoustics noise mapping in more detail, and also your daylighting and sunlighting assessment. So off a single model, we can undertake these processes together, and we are now learning how to adapt these models as a project develops. So I'd like to introduce just how this is done. So this is the acoustic model, and you can see that actually out of all the models that we've got, it's the simplest model. Basically, it's in SketchUp, and we then import SketchUp into various tools to enable us. If you look at the thermal model is slightly more complex in the sense that you've got the shading, you've got a few more buildings and spaces within the building, and the daylighting model is effectively the same model, except we start adding additional parameters to adjacent buildings to include for reflected light. So fundamentally, from the beginning, we can start to shape and analyze models, and it's about the way that we put it through various bits of software that enable us to go fast at the beginning. And then that brings us back to this key slide, which we'll see a few times, which is about how do we balance these components together. And by having models, we can quickly and easily change these components and establish what is the difference between various options. So these are our core aspects. Bringing a balanced approach, early and detailed modelling. This is especially important whenever you've got an acoustics issue on a site, and our desire is to really drive for sustainability. The advantage of sustainability is it also comes with costs. So we're often running downhill as opposed to uphill when it comes to sustainability. So as Usman described, this is a project. This is actually one of Usman's jobs. It's a very nice project in the sense that it's got a garage on the basement and it's got a two-story, sorry, not a two-story, 2 apartments on the floor above. So the challenge here is that we've got actually quite a busy road affecting the facade here, and therefore can we or can we not open the windows? If we open the windows, we end up with a sustainable design. And then the second issue that we had is noise breaking out from a garage, also affecting the noise levels at the facade. It's a reasonable sized garage. It's got quite a lot of activity. So we went there and we measured the noise levels, and then we started to produce some models. So this is the issue of noise transferring across. And we take this approach of early modeling, balancing each early modeling here and balancing each of the disciplines. We've clearly got an acoustics challenge. So this is a section through the building. What we have here is the roof. This was going to come off and the extension is going to go on the top. So the first thing that we did was we built a model of the space, as you can see here. This is a sound source generating approximately the same sort of levels that we were expecting inside, and you can see how the sound bleeds out. But you can also see how once you're past this point here, there isn't actually much sound coming back into the building, which then gave us promise that we didn't need necessarily to do anything special to quite a noisy environment and then protect the residences above. Of course, what we're seeing there is model data. So we like to demonstrate that the model data is correct. So in here is the garage. We've got some sound sources here. We've calibrated it. And then we can actually assess how much sound is coming down. So you can see in here we've got 100 decibels, and here we've got minus 24 decibels of reduction. And that's a considerable level of reduction, which offers us to think about using openable windows in this area here. From there, we started looking at the modelling. So here, this is a modelling tool that we developed with Southampton University. Here's the sound source. You can see it expanding out. This is a reflection of the soffit. So you can see it reflecting within the building, effectively creating reverberation. And now you can see it starting to leave. And sound doesn't unfortunately travel in a straight line, because therefore it would just travel in this direction. It actually bends, and you can see the bending action here. And you can see it reducing as it comes up, and then reducing again, and still reducing further as it moves along the building. We were also interested in the road noise, and you can see how the road noise is different at the different elevations. It's pretty noisy along this elevation here. But you can see that by the time you get on top of the roof, you're losing even more sound energy just by selecting your window locations. So this is the thermal model, and originally these lights weren't in place, and these lights were put in place such that we could ventilate the bedrooms from a quiet location as opposed to the daylighting location. Also, these had the advantage of bringing daylighting into the back. And again, this was undertaken through a relatively simple one model approach, and then a more detailed thermal model has been produced, which is what you see here. The second thing that we did was we also opened up the rear of the building considerably more to prevent overheating, and the advantage of that is it draws the air through the building, allowing us to keep the windows to the living room on the front elevation more closed than necessarily needed to be if it was single-sided ventilation. So by reducing the openings, we're reducing the noise bleed coming into the building. So again, we've taken a balanced approach of looking at daylighting on this particular project, looking at SAP calcs, looking at the thermal assessments under Part L. We've done early modelling that convinced the client that the investment in some of this modelling was worth it. We clearly have an acoustics issue, and we've ended up with a more sustainable building because we're not using mechanical ventilation to provide the cooling in the summer. And then these are basically the services that we provided for this project. And I think now it's time to hand it over to Josh, which will talk to you about Gascoigne Phase 2, which is a £140 million project. And what I particularly want to emphasise on this job is how we, again, undertook very early modelling. That modelling steered us into the building form and the building shape. We then undertook more detailed modelling, understanding the acoustics. We once again undertook some more acoustic measurements, and so on, and developed the project in a tandem, coherent manner.
So yeah, and it's basically just to carry on from that. I mean, we're applying the same principles as we applied for this, than what we applied for the Autotech as well. So it's similar levels of complexity, even though the scale is much larger. So this is a project we were asked to join. There was a previous design that was found to be too expensive. There was also some concerns with some of the design elements, and that the openable windows designed during the summer for cooling didn't take into account the external noise levels. So there was a risk of occupants having their sleep disturbed in the summer when having to ventilate to provide thermal comfort. There were also some restrictions in terms of energy use, so we had to make sure we had a 40% betterment above Part L, and we also had a very quick turnaround. We had to get from stage 1 to 3 in 3 or 4 months. So again, we applied the same approach. So looking at a balanced approach, how can we make sure that people are still being able to sleep properly during the summer? So making sure that they're getting good acoustic comfort and good thermal comfort. You don't have to compromise between the two. And how we can do this is by doing a lot of early detailed modelling, looking at different options, essentially giving the team a little bit more confidence in the decisions being made as well. And that means looking into acoustics as well. So what tricks can we play with acoustics and being able to boost the performance of the facade? What tools do we have at our disposal? And looking at sustainability and cost. So one of the reasons the design was taken back to stage 1 previously was because it was too expensive. So how can we look at passive options which inherently are cheaper and also have less embodied carbon as well? So looking at the site, we have a number of blocks. So the main blocks located on the right and the left here, so block F1 and E2. We've got a noisy road at the north of the site, so that's high levels of noise on the facades, all facing on this road. We've got a number of quieter spaces to the south. So this works out quite well for us in that we have the more exposed facades facing south, but that is actually in a quieter location. So you've got a south-facing facade, you're probably going to need more open area in your windows to cool it in the summer. But actually it's a lot quieter, so having an open area may not have such an impact on your acoustics. But we did need to be careful about a lot of these facades near the road, and making sure that there was a balanced approach in how that was assessed. So we did some solar assessments of the building just to see what kind of options there are available in terms of the shading. So you can see kind of there that there's a lot of shading in the courtyards, and that actually has a beneficial approach for the acoustics too. We looked at a couple of options here as well. So instead of the courtyard approach, it's 2 parallel blocks. You can see that this one's a lot more exposed. You're going to have a lot more overheating issues throughout the whole building, because you've not really got any sort of passive shading from the building envelope itself. As I talked about before, we did some acoustic modelling as well, and as you can see here, the courtyards are very effective in producing nice quiet zones. And, if you can get a cross ventilation approach across some of these, you're able to ventilate with larger open areas in here because it's a lot quieter, and limit what you've got on the noisier facades. Again, we looked at it for 2 options. You can see that the 2 parallel blocks did not really provide the same level of reduction as the previous one with the courtyards. So this was the option that got taken forward. So we start looking at window selection, and based upon data from Napier University, we've got some information on how the orientation of a window against the noise source will affect the performance. So what you can see here is the noise source shifting location. So this is the external facade. You can see how when the noise changes direction, you've got an outward opening window here, inward opening window on this side. You can see how the level of noise changes. I'm just going to play that again so you can see it. So you can see that the if there's a line of sight into the room, you've got high levels of noise, but the outward opening window here then starts acting as a screen against that noise source, and you start getting a lot of acoustic reduction from that. And you can see how much the noise levels drop off. So obviously the darker blue colours, there's a quieter noise level than the green yellow. So and you can see on the left here that it increases more as you've got more line of sight going into the space compared to earlier on when it's lower down. So you can see from this that angling a window correctly against the noise source can actually give you a really big increase in the acoustic performance, and how that can benefit the design and give you more flexibility with open area that you need for cooling. So again, this is just some more data from Napier University and in choosing the right windows, and you can see that there's a bit of a reduction in noise levels depending on the angle. So this is a side hung window if you're struggling to see that. So it just reiterates the previous point. So how can we apply this on a project? So this is a zoom in on one of our noise maps. We've got a canyon along the side here between two of the blocks, and you can tell this is very much a directional noise source. You've got noise coming from the road and it's traveling in this direction, and then going and hitting the facades along here. So how can we use these windows to our benefit to make sure that we get the better performance and therefore can increase the amount of open area that we have? So looking at a few window types, you know, we can play around with different window types and seeing what's the best option that fits the design. One thing we need to be careful of as well is, you know, what is the open area we need to get it to pass the TM52, TM59 overheating criteria, and how can we achieve that open area but also get the sound reduction that we need for the acoustic performance. So again, we did some more finite difference time domain modeling. So that's the in-house software that we have, looking at the options. So you've got this top row here is just a standard openable window. And then we looked at how we can increase the performance by adding a baffle in front of the window. So you can see here we've got a short baffle here with a gap of 175 millimeters from the glazing. And then we have a larger gap, again with a baffle at 250. And this is just a time frame, so this is earlier on. So a noise source traveling from the right to the left. And you can see how it hits the facade and breaks in. So you've got more noise breaking with no barrier, and then you've got reasonable sound reduction, including with the baffle for both options. There's not really that much difference between the two, so that suggests that we can go for 250 mil without any sort of major impact on the acoustic performance. To quantify this, I mean, it's a large project. This is all sort of experimental data that we've got. We wanted to quantify it with some on-site testing. So at the University of Bath, they have a on-site testing facility that we can use. So we set up some tests to see what the impact of the baffle would be. So looking at a window with a baffle in front of it and what acoustic performance that would provide, you know, making sure that we've got the right width and height of the baffle. We just use timber here because acoustically it doesn't really matter what you've got. If as long as it's a solid element, you can have timber, you can have metal, glazing, something like that, all has the same performance. I mean, again, this is something that we talked about with the architects earlier on in the design stage, and you know, using previous examples of how we can build on what's been done before. So having a baffle in front of the window and having an open area on the side here. So these are the results of the testing. And so what we have here on the right-hand side is the acoustic performance without a baffle for different open areas. And then once you add the baffle in, you can see that it jumps up by 8 to 10 dB. So you've got 10 dB for the smaller open areas and then 8 for the larger ones. So it's a really quite a significant improvement. You know, an 8 dB increase will increase the number of windows that are eligible for natural ventilation by a large margin. So this then allowed us to sort of really apply this natural ventilation to the scheme. And by doing this, we're careful not to impact on the daylight performance. So any additional baffled window was added in addition to the window existing window specification. So you would have the window specified as just these 3 elements here, for example, and then adding that extra panel on the side means you don't impact the daylight performance, and you still get your acoustic reduction across that window. There is some impact upon the energy use, because obviously your glazing has a lower U value than you would for an external wall. But this was all done in tandem with the Part L calculations that we were doing. We could clarify that actually the performance isn't going to be too significant and won't affect the energy use predictions. We also did some daylight calcs for looking at balconies and looking at the shape of balconies. So obviously you want a lighter yellow color on this. The darker elements of the facade here indicate sort of low levels on light where you might have to have extra glazing. So we could see that, you know, having an angled balcony on the side of the facade is much more beneficial for daylight rather than having a corner balcony where you get really dark areas right in that corner. So sort of guiding the architect on that as well, and how to design balconies. Looking at the thermal design as well, making sure that we can sort of look at all the options available. So an important part of having a balanced design is not making sure that your open area has to be massive. So making sure the thermal design is running efficiently as well as the acoustic design. So, you know, what tools do we have at our disposal to minimize the open area? So things like thermal mass, cross ventilation, reviewing what the G value can be for the glazing. So, you know, how can we limit solar gains? And of course, looking at glazing area as well. So cross ventilation, you know, what are the options for cross ventilation? How can we incorporate it in our scheme? You know, making sure that we have lots of dwellings located on the corner facades and being able to cross ventilate that. One of the issues with a thermal model is that the bedrooms have to be closed and have their door closed at night. So if you do have cross ventilation during the day, even at night, you're going to run into difficulties because bedrooms have their doors closed and it's essentially a single-sided ventilation scheme. So one of the options we thought of improving this is adding cross ventilation above spaces. So if you can have a ventilation opening through the wall which has an acoustic performance, that allows you to have your cross ventilation during the night as well as the day, giving you a lot more flexibility and a lot more efficient design. Then looked at a few options for different options for, you know, having a ceiling or concrete soffit, different MEV systems, and having a sealed facade. You know, important thing to show here is that with a sealed facade, some of the flat types that we looked at, we took a sample of flats. Some of them were sealed and weren't able to achieve TM52 or TM59 overheating criteria. So we had to be careful about saying where we can seal facades. It might be possible on some of the really noisy facades, but a lot of the other rooms we had to make sure there was a natural ventilation option available. So what that means is we were able to talk to the design team and guide them through a few decisions. You know, thermal mass wasn't an option for a number of reasons, but you know, how you can use the balconies to provide shading and acoustic screening as well, making the most of the dual aspect flats. They didn't want to go for the crosstalk attenuators between bedrooms, but that is something that we're keen to try out in different projects as it's quite an effective passive tool. And then these are the options at the end. So basically looking at each option for the room layout and looking at how using the massing of the site and what elements we can put on the facades to improve the acoustic and the thermal performance means that how we can look at what percentage of the facade is suitable for natural ventilation and what percentages will need to be sealed and have a mechanical ventilation system. So you can see here that you've got option 1, even though it has large areas of low noise levels because there's quite a lot of the building situated away from the road, you still have high levels of noise on a lot of facades, which means that there's going to be that extra reliance on MVHR and mechanical ventilation, whereas option 2 gives you a much more well-rounded result. Even though there were some elements in noise levels between 60 and 65 on the outside, we're able to look at options for natural ventilation still with our baffled windows and ventilating on the quieter sides inside the courtyard, which means that there's only going to be a much smaller area which has to rely on MVHR and mechanical ventilation. So again, just a balanced approach, how to look at this in detail. So doing the thermal, daylighting, part L, acoustics all in one go means you're able to make decisions with confidence, knowing that if you change the shape of the glazing, it's going to affect everything else, and knowing how it's going to affect it, which again links to the detailed modelling and being able to have more confidence in those decisions. Using acoustic tools effectively, so what modelling is available, what kind of elements can you add onto the facade to improve it, and just having a focus on passive design, so making sure that you don't have to resort to mechanical ventilation. First off, you can look at more more passive options, so different window types, different ways of cross ventilating and things like that. And that's us on, I think, 30 minutes on the dot. So thanks for listening, and I guess happy to take any questions.
That's great. Thank you so much. That's some really interesting insight into those two projects, in particular the second one. It looks like it was used up a lot of time, thought, and resources from the office.
It did, but I think that what we were trying to say is that actually it's the same problem, and you got almost an identical approach on both projects. And I think both projects benefited, obviously there's a scale difference, but both projects benefited from a similarity. And I think it's important not to keep this type of work exclusively to large projects. It's more about, how do you set up a system? I mean, you're right, the bigger project takes longer. But a lot of that is in the communication, and a lot of that is also in the thinking, because you have more problems, if you see what I mean, and more variety.
Yeah, no, definitely. We've got quite a few questions, so I'll just jump straight into that. So, for example, we've got a question from Chase, but also I'll tag on James's response, I believe. Should acoustics be thought about more earlier stages of design within relation to building orientation and so on, to create a more sustainable building? And then I believe the response is here, but I think it's valid to include that. I think where required, they are usually flagged up at planning stage. I think that would obviously should have a lively response, I guess, because both of us ourselves have had experience in waiting for the planning stage and seeing what happens.
I think the whole essence of what we've been trying to talk about is the benefits of appointments, I guess, that are loaded more to the front than to the rear. I mean, planning is about preventing mistakes. It's not actually about ensuring good quality living accommodation. Thermal comfort and good acoustics is about ensuring that. And I think that acousticians were once upon a time appointed very, very late on projects. I don't see that as an issue anymore, but what we're trying to demonstrate to you in this presentation is the advantage of being there at stage 1 and even stage 0.
Mm-hmm.
And the advantage that you can bring together, especially if you've got a noise issue, you know, once the building form has been established, it's going to be impossible for an acoustician to change that building form, if you see what I mean. And yet, considering acoustics during the building form, took this project, which is a large-scale project, from uneconomical to economical. So I think that would be my answer.
Yeah, I think you know, if you wait until planning stage to get an acoustician appointed, you know, especially after planning, there's not much you can do on the facade. So there's not much. If there is an acoustic issue that's outlined, historically, it has just been that you go for mechanical ventilation, because there's not much more you can do to the facade or building massing at that point. So which we find frustrating. So yeah, we definitely want to get involved earlier, so we can look at the other options available to the scheme.
Okay, so I've got a few more. So I'll start with Paul's and Meryl's. Meryl's asked, could the baffles not be glass too? And Paul has asked, why was MVHR not a consideration in this project?
So that's 2 separate questions. So the first question with regards to the glass is, yes, it can be glass. The choice actually was for the architect not to go for glass on the grounds that additional heating and architectural language, they wanted to have some colouring up the side of the buildings, if you see what I mean. I think the MVHR, I'll hand this to Josh, but the MVHR benefits a project from not dumping the heat at winter time, and you size the MVHR for that purpose. If you're then sizing the MVHR for summertime cooling, you're burning energy as opposed to saving energy. Yes, you can use the MVHR unit for cooling, but you're much better off doing that naturally and doing the wintertime heat recovery through the MVHR unit.
Yeah, so that, I mean, just to reiterate Ze's point, yeah, that's exactly it. I mean, the reason we used MEV systems instead of an MVHR was that, yeah, it was being priced for this boost mode over the summer, and it was just costing too much for the project for an MVHR system. So we looked at MEV systems, which were a lot cheaper and a lot easier to install, and other options in more sort of looking at the facade in terms of how we can reduce the energy difference in that. Obviously, it doesn't have the heat recovery during the winter, so offsetting that with you know, this scheme had a district heating network as well, so there's already high performance in that regard. So it's just looking at elements of the facade and how we can improve it further.
I think it's a question of, in the main, I mean, we've got some other projects, some large-scale projects coming up in Bristol, where you know, really it's the summertime cooling that is killing the MVHR units. You end up with some really large units. They then produce noise themselves. You then have to store those units within cupboards as opposed to ceiling voids in the case of student accommodation. And just trying to be a little bit more flexible. I mean, it's a very good question.
Okay, we've got a couple more, and then we'll wrap it up with just a quick update from yourselves, and then I'll just represent the couple of talks that we've got coming up. So when producing ventilation strategies that work with acoustic solutions holistically, is it easy to navigate material decisions with other design teams? And same question, do you produce many models with different material options?
I mean, one of the things with the baffles was quite interesting is that the architects were very keen not for it to look like a afterthought on the side of the facade. So they wanted to make sure that the baffles looked like they were designed from the start, which they were, and not just tacked on at the end to deal with any sort of overheating acoustic issues. So we had a few iterations of modelling for that to make sure that they wanted to fit it flush with the facade. So we originally wanted to step it out so we can get more open area. So you know, looking at that, there was definitely a few iterations to get to that point where everyone was happy with the proposed design and and that the architects were happy with what it looked like. I don't know if there's anything you want to add.
Yeah, I mean, I think the one thing that's important to understand is material selection and these sorts of things is often about just changing the parameters of the material in a model and then just pressing go again. And, you know, most times you're waiting less than 5 minutes to get an answer. The trick is then in communicating that and not over modeling, because then you'll put out an incoherent story, which is then difficult for design teams to follow. You can do these sorts of questions often in a more smaller group or an architectural question, or if somebody's got a particular desire to look at something. Yes, I mean, the answer is I think is a good question, and I think that's exactly what we're trying to do. Instead of saying, well, it's likely to make a difference, well, let's chuck a load of mathematics at it and see what the mathematics says. And then if we're not happy with the answers for the mathematics, actually do some experimental work and cross-correlate the mathematics to the experimental.
Great. And then the final question is, what software do you use generally and when modeling, etc.?
We use lots of different modeling. I mean, we're on the thermal and lighting side on IES. On the acoustics, we use Cadna, and we've developed our own software, which is the one that visualizes the sound, which is called finite time difference modeling. And that was implemented with a couple of students down at Southampton University. It's a beautiful bit of mathematics. It's quite complicated, but it's remarkably useful. I think it's not necessarily the tool that you're going to use, it's the strategy that you're going to use, and the one model approach. Though it sounds simple, again, I think Sujitesh, we saw join the talk, that was Sujitesh's dissertation probably about 3 or 4 years ago at Bath University, is how can you have interoperability between different software packages. And it's not difficult necessarily to achieve it. It's the philosophy of how do you work with a team and inform a team, and also how do you pay for it from a consultancy perspective, because you can end up running more models than some of your competitors and you're not going to get more money for it.
Okay, great. Thank you for that. Just to wrap up, I'll take over and share my screen with the intro page. So you've just had a talk from Ze and Josh from MACH Group. It was our CPD in 43 presentation, Optimizing Building Physics Design, where they looked at 2 very contrasting projects and gave really good insight into sort of the similarities in regard to the 2 projects, and in essence how much an acoustician brings to the fore when looking at site development right from stage 0 all the way through wherever they may be coming in. I know Ze's mentioned the potential for offering additional talks. So Ze, if you could just fill everyone in on that.
Right. Just talking about that. So I think you know what we've done. It's quite difficult. We had a debate just before presenting this as to whether what we presented is sufficiently educational. I mean, we both teach at Bath, and we have other people in the office that teach at different locations and on different courses, and it's something that I think is very important to MACH, sharing of knowledge, but it also, I think, enables us to work better with our teams, and you know, the more our design teams understand, the better we move forward. So we have on a regular basis undertaken full day presentations to people, architects. I think we've taught several offices at Wilmot Dixon, their entire team, acoustics and thermal modelling and those sorts of principles. So we're extremely keen to set up a sharing system. Might be a nominal sum, but the money side of that is unimportant for us. It's about sharing knowledge, and those sorts of things is important. And if we can, in these instances, we take more time and provide an awful lot more information as to exactly what's going on with regards to the physics, how the models are built, what are the inputs to the models, and that, in our opinion, is very useful to our teams that we work with.
Okay, great.
We would value the opportunity if anybody's keen.
Okay, great. And then, so bringing that to a close, we've got, obviously, as I mentioned at the beginning, we've got 2 more talks already scheduled in. So please do have a look at the Eventbrite page. View City, which is on the 19th of May, very interesting, looking at 3D modeling of cityscapes and how your potential proposals could be impacted by recent planning permissions or proposals that are yet to be built or are currently under construction, being able to look at them and see how those are impacted. And then secondly, Cinema Works, which are looking at designing home cinema and media rooms. So hopefully these are really useful for everyone listening in. Again, thank you for Ze and Josh for attending the talk and enlightening us on all of the bits that you've just explained to us. Thank you for everyone attending from wherever you have attended, and I look forward to seeing you all soon.
Thank you very much.
Equally, Usman, thank you for inviting us and thank you for organising it, and thank you everybody for attending and giving us your time. Much appreciated.
Thank you.
Okay.
Great.